Good morning and welcome to the class on counters. A counter is a digital system used to count the number of clock cycles. It is constructed by using flip-flops. The number of flip-flops required to construct mod 2 power n counter is n. That is, if you use one flip-flop, you can construct mod 2 counter. If you can use two flip-flops, you can construct mod 4 counter. If you have 3 flip-flops, you can construct mod 8 counter and so on. There are two types of counters, asynchronous counter and synchronous counter. Asynchronous counter can also be called as ripple counter or serial counter. Synchronous counter is called as parallel counter. In an asynchronous counter, the first flip-flop is driven by the clock signal and the output of the previous flip-flop is the clock signal for the next flip-flop. So it is called asynchronous counter. In a synchronous counter, all the flip-flops are driven by the same clock pulse, so it is called synchronous counter. The construction and operation of asynchronous counter is very simple. It requires minimum hardware, whereas a synchronous counter requires increased hardware. In an asynchronous counter, each flip-flop is driven by previous flip-flop and so the counter has cumulative settling time. In a synchronous counter, each flip-flop is driven by clock, the same clock, and thus the settling time is delay time of a single flip-flop. In practice, a combination of these two types are used to compromise between speed of operation and hardware count. If the counter advances by 1 for each clock transition, then it is called count up mode, and the opposite is called countdown mode. That is, when the counter counting decreases by 1, then it is called countdown mode. In this class, you will see the working of asynchronous counters. We shall start with 2-bit asynchronous counter. A 2-bit ripple counter or asynchronous counter uses two flip-flops. The circuit diagram, the timing diagram, and the truth table are given in this slide. In this slide, we shall see how to draw the mod 4 asynchronous counter or ripple counter. The mod 4 asynchronous counter uses two flip-flops. Here we use JK flip-flop. J and K are the inputs. The clock signal is given to the flip-flop. It is the negative edge triggered flip-flop as shown by the bubble here. The outputs are A and A bar, and you use another flip-flop which has inputs J and K and a clock input. The outputs of this second flip-flop are B and B bar. J and K of the first flip-flop are connected to VCC and so it remains in the one state. J and K of the second flip-flop also are connected to VCC and remains in the one state, and this state corresponds to the toggling state of the JK flip-flop. Whenever J is equal to K is equal to 1, the flip-flop is ready to toggle. The flip-flop toggles whenever it sees the negative edge of the clock signal. Now, the clock signal is given to the first flip-flop. The output of the first flip-flop, A, is given as the clock for the second flip-flop. The outputs are taken from A and B. This is the circuit diagram for mod 4 asynchronous counter. Now, this is the clock signal given to the first flip-flop. The numbers represent the number of the clock pulses and the lines denote the negative transition of the clock signal. This is the clock pulse given to the first flip-flop, and we can also draw the timeline of A and B. Initially, when you start the working of the flip-flop, both A and B are 0, 0. Now, whenever the first flip-flop sees the negative transition of the clock signal, it will be toggling. So due to the first negative transition, A goes from 0 to 1, and during the second negative transition of the clock signal, A goes from 1 to 0 state. During the third negative edge, A goes from 0 to 1, and during the fourth negative edge of the clock, A goes from 1 to 0. During the fifth negative edge of clock, A goes from 0 to 1. During the sixth edge, it goes from 1 to 0. During the seventh edge, it will be going from 0 to 1. During the eighth edge, it will be going from 1 to 0. During the ninth edge of the clock, A goes from 0 to 1, and during the 10th negative edge of clock, A goes from 1 to 0. Now you can see that the frequency of A is half the frequency of the clock signal. Now this A is given as the clock pulse for the next flip-flop, second flip-flop. So whenever A is going negative, the second flip-flop is toggling its state. So during the first negative edge of A, B goes from 0 state to 1 state, and during the second negative edge of A, B goes from 0 to 1 state. During the third negative edge of A, B goes from 0 to 1 state. During the fourth negative edge, B goes from 1 state to 0 state. Now if you write the output of the flip-flops for each clock signal, you see that before the first clock pulse, the outputs are 0, 0. After the first clock pulse, 0, 1. After the second clock pulse, 1, 0. After the third clock pulse, 1, 1. After the fourth clock pulse, it goes to 0, 0. If you see the count and write the decimal equivalent, 0, 0 before the first clock pulse corresponds to the decimal equivalent 0. 0, 1 corresponds to the decimal equivalent 1. 1, 0 corresponds to the decimal equivalent 2. 1, 1 corresponds to the decimal equivalent 3, and 0, 0 corresponds to 0. For the next count, it is 0, 1, which corresponds to 1, then 1, 0, which corresponds to 2, then 1, 1, which corresponds to 3, 0, 0, back to 0. So the counting is from 0, 1, 2, 3, then it restarts from 0, 0, 1, 2, 3, 0, 1, 2, 3, and so on. This is the working of mod 4 counter, which counts from 0 to 3, 4 numbers. Next we'll see the working of mod 8 asynchronous counter or 3-bit ripple counter. The circuit diagram is shown here. You use 3 flip-flops. All the inputs, J and K inputs of the flip-flops are connected and given to VCC. So all the flip-flops are ready to toggle during the negative edge of the clock. The clock signal is given to the first flip-flop. A is given as the clock signal for the second flip-flop, and B is given as the clock signal for the third flip-flop. So the timing diagram is shown here. If you see the countings, before the first clock pulse, A is 0, B is 0, C is 0. And after the first clock pulse, from C it is 0, 0, 1, which is represented by this state. After the second clock pulse, 0, 1, 0, which is represented by this state in the truth table. After the third clock pulse, 0, 1, 1, which is represented by this in the truth table. After the fourth clock pulse, 1, 0, 0, which is represented by this state in the truth table. After the fifth clock pulse, 1, 0, 1, which is represented by this state in the truth table. After the sixth clock pulse, it is 1, 1, 0, which is represented by this state in the truth table. After the seventh clock pulse, it is 1, 1, 1, which is represented by this truth table. After eighth clock pulse, all the outputs become 0. So here the counting is from 0 to 7. It is counting 8 numbers. So this is called mod 8 counter. Next, this chip 7493A is a chip for constructing mod 8 counter and mod 16 counter. Now this is the circuit diagram inside the chip. This is a 14-pin chip, and you can see that this is the first flip-flop followed by 3 flip-flops here. When you use this flip-flop alone, then it can be used as mod 2 counter. When you use these 3 flip-flops alone, then you can have mod 8 counter. If you connect the output of the first flip-flop QA to the clock signal of the second flip-flop, then you can use it as mod 16 counter. The timing diagram for mod 16 counter is given here, and this is the truth table for mod 16 counter. It counts from 0 to 15, 16 numbers. So this is called mod 16 counter. L stands for 0 state and H state stands for 1 state. In this slide, you can see the circuit diagram for a down counter. The main difference between this counter and the previous counters you have seen is that in the previous counters, A is given as the clock pulse for the second flip-flop, B is given as the clock pulse for the third flip-flop. But here, A bar is given as the clock pulse for the second flip-flop and B bar is given as the clock pulse for the third flip-flop. So, whenever A bar is going negative, the second flip-flop is triggered. Or I can say that whenever A is going positive, the second flip-flop is triggered. The same way, I can say that whenever B bar is going negative, the third flip-flop is triggered. Or I can say that whenever B is going positive, the third flip-flop is triggered. So when you see the countings for the before the first clock pulse, the outputs are 0, 0, 0. After the first clock pulse, the outputs are 1, 1, 1, which is represented by this state. After the second clock pulse, the outputs are 1, 1, 0. That is shown by this state. After the third clock pulse, it is 1, 0, 1, which is shown by this state. After the fourth clock pulse, it is 1, 0, 0. It is shown by this state. After the fifth clock pulse, it is 0, 1, 1, 1. It is shown by this state. After the sixth clock pulse, 0, 1, 0. It is shown by this state. After the seventh clock pulse, it is 0, 0, 1, which is shown by this state in the truth table. After the eighth clock pulse, everything is 0. All the outputs are 0, which is shown by this. So if you see the counting, it counts from 7 to 0 in the descending manner. So it is called countdown counter or down counter. It is a mod 8 down counter. Similarly, you can construct mod 16 down counter using 4 flip-flops. This slide shows you a 3-bit binary up-down counter, a mod 8 binary up-down counter. You know that this is called the control circuit. We use this control circuit to select any of the two modes. Here, the control circuit selects either count up or count down. The control circuits contain 2 AND gates and 1 OR gate. Count up is given to the first AND gate of the control circuit. Count down is given to the second AND gate of the control circuit. Other inputs are A and A bar respectively for the first flip-flop and B and B bar respectively for the second flip-flop. When count up is 1 and count down is 0, A will be given as the clock pulse for the second flip-flop and B is given as the clock pulse for the third flip-flop. Whenever count up is 0 and count down is 1, A bar is given as the clock pulse for the second flip-flop, B bar is given as the clock pulse for the third flip-flop. So, and when count up is 1, count down is 0, this circuit functions as 3-bit up counter. When count up is 0 and count down is 1, the same counter functions as 3-bit down counter. So we can have both up down counter in the same circuit using control logic circuit. Thank you.